Today, I want to talk to you specifically about graph neural networks and their flaws, limitations, and some improvements that we can make to fix those flaws and limitations. Before I dive into that, though, very specifically, I want to address kind of like why I do what I do on this channel, why I open source everything the way that I do, etc. Bottom line is that like I understand 100% that ticks people off to just open source things, right? That's one reason why I do it. Very frankly, like I love it when I tick people off by doing that. By taking things that there's a like so the modern internet is based off of essentially taking information and trying to monopolize information. That's the Web 3.0 as we know it, right? And that's the Jeff Bezos model. A bunch of people know it. A bunch of people have made money and made themselves successful with that model. I see AI as the antithesis of that model. Like AI actually eats into anyone that derives their income from those types of things, and the person doesn't realize it, right? They're actually like the people that are at the top of that game, like at the top of like the marketing game, sales, and that are just all about that. Like they utilize essentially monopolizing information in like small niches like law or other industries to try to get ahead in those areas just based off of monopolizing information. But what they don't realize is that these tools and propagating and spreading these tools actually diminishes their efforts and what their value more than anyone else's, right? If you take a tool and you have something that like only 1% of people can do, and then all of a sudden 99% of people can do it if they just put in the work, that kills the monopoly behind it, right? And that's the whole point behind it. And that's 1,000,000% exactly why I do these things. Like anything that I discover that is like at the forefront of AI that I think someone might want to put a patent on this, I open source it immediately, like flat out. That's kind of my MO within this, right? And then I'm not the only one, and there's a lot of people. I feel very safe at this point that I don't think any of these patent trolls are going to be able to monopolize AI in any way that they think of, and the way that they're trying to is beyond funny to me. They're setting their money on fire, which is why you see so much money, like so much venture capital money coming into AI. Like personally, why I haven't accepted venture capital money. Like I don't want to directly rip people off, right? I would rather just tell you that you're getting ripped off if you're a venture capitalist or a marketer or someone like that, and you're investing heavily into AI. Like you're burying yourself, and that makes me beyond happy. And so that's why I do what I do. But so let's dive into, in this instance, the limitations of graph neural networks. And then so in this instance, like the bottom line, like so graph neural networks overall, they're great in practice, right? If it were a unicorn world and like academia world, graph neural networks would be the best thing on the planet. The problem is that when you introduce graph neural networks to the real world, they fall apart. And they fall apart on a few levels and for a few different reasons. The primary one we're going to look at here is this graph structure limitation. And then so what this means is that essentially within a graph, when you graph out information, like you expect it to follow a sequence. So it would be like, let's say I have a graph of information of a grandfather to father to son, right? Three, grandfather, father, son. Or we can be great grandfather, grandfather, son, father, son. So we get four. And then within that, we would expect it to follow that pattern, right? Great grandfather, grandfather, father, son. But it doesn't necessarily have to, and the weights won't necessarily do that, right? They might go grandfather, son, father, great grandfather. And if that pattern works and the model is able to sync that, it will do that, and it will build information off of that. So problem number one is that you do that and then you think it will do purely sequentially, but it doesn't end up being the case, and then so your data skews out from there, right? Problem number two, this particular site does a good job of doing that problem, going into that problem, but they don't go as well into the rest of the problems. But so the other problem that you run into within this is like dirty data within your training data, right? So if you have, let's say, two pieces of information, and like a common example of this would be that like you have a document from, let's say it's you have one document from 2018 and one document from 2024. The graph neural network by itself isn't going to determine or differentiate which one of those is like the better one, right? It's gonna pull both of them, and then it might probabilistically do some averaging between the two, etc. But like perhaps like in a lot of instances, and for most corporations, in that instance, like that 2018 version would be severely outdated. Right, and then, like maybe systems that you no longer even use, etc. But to the graph neural network, there's no differentiation between that 2018 document and that 2024 document, and that's a huge factor there. And then the other thing is that these are very susceptible to injection, like injection attacks, like any sort of like hacking attacks. It's very easy because the general structure of a GNN is brittle in that like it's easy to change the model's like perspective. And like here's a good example, right? The noise vulnerability within GNNs. And then so say for example you have an initial sequence, and then you showed a picture, and then it guesses panda with 60% accuracy roughly. And then you just like inject some noise in there, like a noisy attack essentially, and then you'll see that it will like change the prediction to given with like almost 100% confidence, right? And literally all you're doing is you're just doing panda plus noise, and then it's like, for whatever reason, panda plus noise equals given according to a GNN model, right? And that's a very common problem within these models overall. And so like why I don't like them in real world use cases. And then so my common thing on this channel, right, and what I kind of built my career on is so here's the monkey. I'm not just going to throw the monkey on your back. What's the solution to what I just laid out, right? And then so here it is. I went through some innovating to try to resolve both of these problems that I laid out, or all of these problems that I laid out. So this is my version of Graph Data Quality Management System, or a GDQMS. I won't read through all of this for you. I'll leave this like top so you can read through essentially like everything that I put into it. But I put into it a graph data validation layer, a temporal graph reasoning engine, context-aware graph filtering, trust and authority score propagation, and graph-based reinforcement learning. So like overall, kind of what I'm doing is trying to mitigate these concepts, right? I'm trying to like say that like different nodes can have like different weight depending on different factors like trust and authority. So like is it how recent is it? And then you can also take into advantage like context, like trying to add probability to these linear aspects of the GNN network overall. Flat out. Like the thing that people like about GNNs is that they're very linear, right? Which they are, but they're too linear in these instances, which is where you have these problems. So essentially everything that I'm building out here is like really like injecting some sort of a probability around this, right? And then so up front, what I do is I first build out everything around what I just mentioned, and I built it out here in individual cells, and then our end output here is this. So I have like we can see that when I run this to the network is able to like essentially like clean itself, right? It can remove outdated and low quality nodes. It can find and remove conflicting nodes, and then if I like give it like for example some context around a work policy, it can like give like our good like confidence score, and then everything related to that. Like so we get kind of our typical output here that we would get from our GNN model, but essentially what I'm doing before then is like a cleaning up and like essentially like giving the model more tools in this instances, very specifically for like again like outdated policies, things like that. It gives it more weight to the edges, right? It's rounding the edges and the nodes is basically like the simplest way that I can explain that. All of what I do here though up front, that doesn't address the main and the biggest problem that I bring up here in this, which is like this is very hard to deal with in and of itself, right? And then so very specifically, if you get deep into graph neural networks, there are two competing methodologies that try to solve that specific problem. I'm going to lay out one of them for you, which is the Weisfeiler-Lehman GNN network. And then so within this is the more, we'll say like computationally expensive framework within this, but for this particular problem, like the linearity problem, out of the two kind of like competing frameworks that currently exist around like higher level GNN networks, the Weisfeiler-Lehman model seems to solve this particular challenge better. So we'll integrate this into our model here, and then we'll look at the results there. And then so I do that. And then so what we can see here is that it adds like our edges, and it adds connection to the edges, right? Is that like the bottom line that we see here. So we have our individual nodes, like node A, B, and C, as we would, but then we can also add, like, again, connections to those. So we can make sure that our edge is specifically related A to B and B to C, instead of it going like A to C or B to C, B to A, for example, right? We structure it out and we get the ability to literally map out the edge. And that's the big difference there, and what this model provides us to do, as opposed to your typical GNN. None of this solves whatsoever, though, the data problem, right? Like, if you put bad data into these models, then that propagates all throughout the network. And like, whatever data you're putting into these models, it's what it's going to graph off of. And that's like the key limitation within this, right? Like, very first thing is like companies that get into GNNs, they want to just throw their entire database in that. You need to be more selective as to what you're putting into this database than you would with your ERP. Like, this is, you need like a source of truth like you wouldn't believe, right? And you only want to put source of truth in here. And then, like, quite frankly, what I would do is I would build and develop policies up front. If I were building out a GNN under and knowing these things for a corporation, I would very specifically outline this situation up front. I'd build out these types of policies, but then I would also take the additional step of making sure that our internal policies align with this. And then, so what I mean by that is I would essentially, like, I would plan and rebuild the network from scratch, like yearly, right? And then, so I would essentially have like our base data set that we would do, and that would carry over from year to year. And then during the year, then I would also be in, like, on the back end, cultivating what will be like in this instance, like, we're in 2025, we're starting in 2025. So I would start the 2025 data set, right? And then the 2025 data set would be implemented fully in 2026, at the beginning of 2026. And then that model, the 2025 model, would be imploded, no longer utilized, because it would not have, it would have like too much old information, right? I wouldn't want to stack old information on top of it, because I just flat out wouldn't want to give the model these problems that I'm addressing. And then, like, I wouldn't want it to have a policy document from 2010 in there and a policy document from 2024. Just give it the policy document from 2024. And then that alleviates the problem, right? And then if the policy document from 2024 is no longer relevant, then that will be updated in the new model, and the new model will reflect that, and will never have the policy 2024 document within its memory, so you'll never run into these issues. Planning that up front is the best way to deal with this. And then, so, like, I mean, what I just stated is super easy to do. I've never seen a single organization actually do it. Hey, you're a unicorn if you can actually pull that off, which is, like, again, the real world problem within graph neural networks. Like, if we're talking about unicorns, rainbows, and fairies, then graph neural networks are the best thing on the planet. Your data is not made up of unicorns, rainbows, and fairies. It's made up of garbage cans and sludge. And so it's just the way it is, right? And then, so if you put garbage cans and sludge into the GNN, you're going to get garbage cans and sludge. It's kind of the overall result there. But so hopefully this is a good understanding as to GNNs overall, their flaws, and furthermore improving those flaws, and then trying to address and fix those flaws. But again, it all comes down to data is the biggest flaw, and nothing can address that but you. So if you like this type of content, please like and subscribe. Thank you very much.